Hello everybody, this is Diptarka. In this talk, I will present our work on approximate trace reconstruction in the average case setup via median string. This is a joint work with Debarati and Ravi Krauthgamer. Let me start with defining the trace reconstruction problem. So in this problem, our task is to reconstruct an unknown string from its noisy observable copies, which are also known as traces. More specifically, we have an unknown string x, which is of cell length n, but what we can observe is a set of noisy copies of it, the x1, x2 up to xm. And these noisy copies are generated by some probabilistic noise channel. We will talk about that in the next slide. And these noisy copies we will refer to as either traces or samples. And our objective is to get back x. And we want to use as few samples as possible. Second, we want to minimize the estimation error while recovering x. I will talk about what type of error we'll consider later. And of course, we want the reconstruction procedure to be very efficient. So here is the type of noise that we consider. So there is a probabilistic noise channel. So this unknown string will pass through it and it will generate the traces. So there are several types of noise channels. So the most simplest one is the substitution channel, where each symbol is flipped with probability p. So this p is a noise parameter and it is associated with the noise channel. So the substitution channel, as I mentioned, is the most simplest one and is very easy to handle for the trace reconstruction problem. Now the most challenging one is the deletion channel, where each symbol is deleted with probability. Now perhaps the most challenging one is the insertion deletion channel, where both insertion and deletions are allowed. So here the noise channel will scan symbols of x one by one, and while scanning, it will keep the next symbol as it is with probability 1 minus p. It will delete with probability p by 2, and it will insert an uniformly randomly chosen symbol with probability p by 2 before the next symbol. Now, as I mentioned that this insertion deletion is perhaps the most challenging one, but I should also mention here that one can also allow substitution operation in this channel. So there could be a channel which has everything insertion, deletion, and substitution. And also this probability p by 2 and p by deletion and insertion probability, which we have written here p by 2 and p by 2, that could be there could be different deletion and insertion probability involved. And in that way, we can get the most general version of the noise channel. So, but in this talk, we will consider this insertion deletion channel where the deletion probability and the insertion probability are the same. But I also should mention here that all our results actually could be extended to this more general one where the substitution is allowed and the deletion, insertion probability and the substitution probabilities are different. So now, for trace reconstruction, there are even two types, or we can categorize this problem into two cases with respect to the unknown string. So the first one is the most general one, which is called worst case, where the unknown string is arbitrary. And the second one is the average case, where the unknown string is chosen uniformly at random. And as you have already seen in the title, that in this whole talk, we will only consider the average case. So now, what are the applications of trace reconstruction? So there are actually several applications of it, but I will put slightly emphasize on this first application, which is DNA-based storage system, which is new technology of storing big data, where the data are first encoded as DNA sequence, and then they are stored in the database. And while getting back that data, we will use some kind of next generation sequencing, and that will generate several noisy copies. And here the noise is exactly the insertion deletion type of noise. And then the objective is to get back X, which is exactly same as the trace reconstruction problem. And also in this particular case, it is the average case essentially, because in the encoding step, what people use is that in that DNA sequence that we are going to store in the storage space. So that particular sequence is randomized using some sort of pseudo-random sequences. So that's why the initial stored data is some sense random. I mean, stored sequence is some sense random. So that's why it is essentially the average case version of the trace reconstruction. So this problem also has other applications in computational biology, and we will not talk about that in this talk. So now let's proceed with our result. So, but before going into our result, let me talk about what is known about this problem. So for the average case version, it is known that there is the upper bound of exponential in order log to the 1/3 n traces that says that this many traces suffices to reconstruct the unknown string with running time almost linear in n. On the other hand, it is known that to reconstruct it exactly, we need at least log to the 5/2 n traces. Now you can see that there is a huge gap between the upper and lower bound. But both these results are for exact trace reconstruction. So one of the open problem is, can we close this gap? But today we will not go into that direction. We will take a slightly different direction, and we will ask the question of approximating the trace reconstruction. So that's why the question is, what about the approximation? Because many application doesn't need the exact reconstruction. For example, this DNA storage system, it is fine to actually reconstruct something which is very close to the stored data, because we use error correcting in the pre-processing step. So that's why it suffices to get back something close to the original data. So yeah, so that's why, I mean, it suffices to recover a string Z that is close to unknown string. So now what type of closeness we should talk about here? So there are different measures of closeness among strings. So either we can take Hamming distance, edit distance, but we find the edit distance is the most natural one, because the insertion deletion channel, so there the errors are edit errors. We perform insertion and deletion. So that's why it is natural to consider something that counts the number of insertion and deletion operation. And that is why the edit distance is the most natural one here. Is, I mean, just to remind you, the edit distance between two strings is the minimum number of insertion, deletion, substitution operation required to transform one string into another. But in this talk, when we consider the edit distance, we will not consider the substitution operation. And as you can guess, the reason is because our channel is just insertion, deletion. We are not allowing substitution. To make everything symmetric, I mean, we just consider insertion, deletion in the edit distance. I mean, now the substitution operation, you can think of like one insertion and one deletion. So it will be two edits. So now what we can now say about approximate trace reconstruction. Well, so one trivial observation is that if we output one of the input trace, then that will be close to the unknown string. And how close? It will be of edit distance at most roughly Pn, because P is the noise parameter. So that's why roughly Pn many edits will happen. I mean, there will be some 1 plus delta term involved here, but that we will ignore throughout this whole talk. So now the natural question is, can we do something better? Can we reconstruct a string that is much more closer than this distance Pn? So here is our main result. So we show that using 3 traces, we can recover a string Z, which is of distance from the unknown string X of distance P square log 1 over Pn with high probability. And we design a deterministic algorithm that runs in O tilde in time that will output the string Z. And now you can say that I want to emphasize that on this number of traces required. So here we need only 3 traces. But if you recall in the earlier slide, we have seen that for exact trace reconstruction, we need at least omega log to the 5/2 in traces. So this is a sharp contrast with the exact trace reconstruction. And also, I mean, throughout this whole talk, we will consider the binary alphabet, because somehow the binary alphabet is the most challenging one. So for example, if we allow larger alphabet, but some constant, large constant size alphabet, then actually we can even get rid of this extra log 1 over P term. And we can get this Z, which is of distance P square N. And this P square N bound is in some sense tight for 3 traces. We cannot get anything better than that. So now, before explaining our result, let me define another problem. It's the finding median string problem. So in this problem, we are given a set of string. The objective is to find another string Y, not necessarily from the input set S, that minimizes the following objective value. So the objective value is sum of distances to the string in the input set. And suppose Y star be the string that minimizes this objective value. We call this Y star median of the set S. And so this median problem is a well-defined or well-known problem used in the data analysis, and it is defined over any metric spaces. But in this slide, we define this median with respect to the edit distance. And even with a general metric, this median problem has several applications, but we will not talk about that in this talk. So this median string problem is known to be NP-hard, but there is a standard dynamic programming algorithm which finds it in 2 to the m times n to the m. So basically exponential in m, where m is the number of input strings, each of length at most n. And it is also known that under strong exponential time hypothesis, we cannot improve that algorithm much. More specifically, we cannot get order n to the m minus epsilon time algorithm. But what about approximation? Can we do something better? So let's just quickly define what do I mean by approximate median. So suppose opt is the optimum objective value attained by this median string Y star. Now a string Y bar is a C approximate median if the objective value with respect to Y bar is at most C times the optimum objective value. Now can we get a constant factor approximation in polytime? Well, so that 2 approximation is not difficult, because if you take the best input string, so basically the out of the input set S, so whatever the string that is the minimum objective value, if you output that, it's not hard to show that that will attain the 2 approximation. And this will work for any matrices. It has nothing to do with edit distance. So now the natural question is, what about the PETAS? Can we get a PETAS for median string problem with respect to edit distance? Or even like breaking below 2. Can we break below 2 in polyton? So we don't know any answer to that question. But now, I mean, you may wonder, I mean, why I'm talking about this median string problem where our main result is on trace reconstruction. So is there any connection between these two problems? Well, a common heuristic for trace reconstruction in practice is to find a median. But so far, there's no definite connection between these two problems. So one of our results in this paper is that these two problems are essentially the same, at least in the average case. More specifically, suppose y bar is an 1 plus epsilon approximate median of the strings x1, x2, xm, which are generated from x by an insertion deletion channel. Then with high probability, the edit distance between this unknown string x and this approximate median y bar is order epsilon times opt by m, where m is the number of input strings. Okay. So what's the use of this result? I want to claim that actually our main result that we have presented before, the result 1, actually follows from this result 2. How? Let's see. So this was our result 1, that we can get back, we can reconstruct this x. We can get a string c, which is of edit distance p square log 1 over pn with high probability. Okay, so now let's see how our result 1 follows from result 2. So for 3 traces, x1, x2, x3, the opt value is at most 3 pn. Why? Because p is the noise parameter. So with high probability, each of the traces is of distance at most pn from x. Again, I mean, there will be some 1 plus delta factor, but for simplicity, I will ignore that term throughout the whole talk. And thus the objective value from x is at most 3 pn. Then obviously opt is also has to be at most 3 pn. Now just replace that quantity. Recall that in our result 2, we have shown that x and y bar, the edit distance has to be order epsilon times opt by m. Now here m is 3, and now epsilon is some constant times p log 1 over p. So then we get this result. And now this y bar is an 1 plus epsilon approximate median. Now if you can get an exact median, then obviously this bound will also hold. Now recall that using a standard dynamic programming, we can compute an exact median in time exponential in the number of inputs. Now here the number of inputs is only 3. So the running time is just n cube. So we can reconstruct an unknown string x approximately with distance this p square log 1 over pn in time n cube. Well, but our main result was that we can reconstruct in near linear time, O tilde in time. So the one question is, how can we improve this running time from cubic in n to linear in n? So here is the idea. So to achieve the near linear time, so we first divide the input string into small blocks and then compute the median for each block independently. And then finally concatenate those block medians. So here is the intuition. So suppose here is the unknown string, and these are x1, x2, x3. And now I First partition the unknown string into equal size block. And then for each block, look into which portion of it in the trace is generated from that block. Okay, so in this, this portion of x1 is generated from this portion of the unknown block. And that is how I divide x1, x2, x3 as well. So for simplicity here, I partition x1, x2, x3 also equally. But since the noise channel is insertion deletion, that need not be the case. So now I compute the block median. So now apply the blockwise, our result to blockwise. So now for each block, this of C and X by result 2 has to be close enough. And if each of these blocks are close enough, then of course, as a whole, they will also be close. But the challenge here is that how do we identify them? Because we don't know X. We only have x1, x2, x3. So how do we know that which portion of the block of x1 will corresponding to which portion of x2? Because as I mentioned that they may not be evenly partitioned in all the traces. So to mitigate this issue, what we have done is the following. That first take one of the traces, say x1, and take some small size anchor. Okay. So we take anchors of size log square n, but between the two anchors, we keep a buffer space. Okay. So now for each of the anchor, find the best match in x2 and x3. So when I say best match, basically I mean that we find the closest substring of each anchor with respect to edit distance. Okay. And then just find the median of these blocks and concatenate them. Well, so now why it works? So first, let's see. So for each anchor, look into its corresponding block in X. Okay. So for this anchor, this is the corresponding block. That means from this block, using insertion deletion noise, I get this particular. So now for this particular block, let's see what are its corresponding blocks in x2 and x3, which we refer to as true matches. Say these are. So for this one, these are the true matches. And then for the last one, these are the true matches. What we want to claim is that for each anchor, these true matches are actually very close to the best match. So I will not talk about the proof. I will not provide the proof here. But in the proof, we crucially use the fact that X was chosen uniformly at random. So now it basically says that finding median for the best match block is almost same as the finding median for the true match block. So ideally what we want is the finding median for the true match blocks, because then we can, just similar to our first, earlier slide, that we can apply our result to blockwise. Because if we find the median of this one and the true matches, then whatever we get, then we can compare it with this particular block of X using result 2. But now instead of true matches, we have best match. But since they are close enough, essentially their output will be same. And that's why still we can argue that the C, the one block of C will be very close to that corresponding block of X. Okay. And also we keep the buffer size to be omega log n, and that will help us to keep these two different blocks to be well separated. And that will also be crucial in arguing that each of these blocks that we will reconstruct will be independent. And that's why we can compare just independently with each of these blocks. And also another fact is that we will keep the buffer size smaller compared to the anchor size. And that's why, since you can see that finally we ignored these buffers. So in this concatenate version, there is no place of buffer. So since the buffer size is much smaller compared to the anchor size, so that will add up a small quantity in the error, in the edit error. And that's essentially the end of the correctness proof. And now what about the running time? You can see that since the anchor size is log square n, there are at most n by polylogs n anchors. And now for each of these block, when we compute the block median, so block size are of log square n, right? Roughly, so this anchor is of size log square n. So now computing the median of this block, and this block, these three blocks, take only polylog n time. So that's why now, since there are total n polylog n anchors, and for each of them I take polylog n time, so the total time is just O tilde n. And that's the end of the running time. Okay, so now we get our result 1. So now, before concluding the talk, let me talk about a few concurrent works. So for the deletion channel, this is a work by Jane, Day, Lee, Sarvideo, and Sinha, who gave that for the using any m, where m is less than 1 over p. So using any m traces, we can reconstruct up to edit distance n times pm whole to the omega m in polytime. And this edit distance bound is almost optimal information theoretically. That is what also they have shown. Also, in another concurrent work, Hayes and Perez, they show that if we want to achieve edit distance epsilon n, then exponential in order log 1 over epsilon whole to the power 1 by 3 traces are sufficient. Okay, so now let me end this talk by posing a few open problems. So the first one is that, can we reduce the error by using more traces? So in our results, if you recall, the number of traces were 3. Now, can you get, can you use more traces and reduce the error? So you would like to conjecture that the edit distance between x, the unknown string, and the approximate median y bar could be reduced to epsilon n for arbitrary small epsilon using poly 1 over epsilon traces. And if this conjecture is true, that directly gives us an approximate trace reconstruction algorithm where the output string z will be of distance at most epsilon n for arbitrary epsilon. And then the second one is, can we get a similar result for the worst case trace reconstruction? Because so far, whatever we have presented, everything holds, everything are crucial using the fact that the unknown string was chosen uniformly at random. Now, can we get something similar when the unknown string is arbitrary? Okay. So if you have any question, please attend the Q&A session in the conference. Thanks.